Hello everyone. In the last class we have seen the concept of super mesh. So, it is again a mesh analysis only, but the concept of super mesh is considered whenever a current source appears in common to two meshes. And there was an illustration in which we observe that whenever a current source appears in common to two meshes, by considering the concept of super mesh, it will reduce the number of steps involved in obtaining the solution for a problem, right. So, now we will take up a problem related to the concept of super mesh. Now, here is the problem. So, use mesh analysis to find Vx. So, Vx is available here in the circuit shown in figure 21. So, this is the figure 21, and the same problem has been copied to the board, okay, and now our objective is to find this Vx and using mesh analysis. And the first job what we need to do in the mesh analysis is to identify the meshes and the corresponding mesh currents. So, this is the mesh 1 wherein I1 flows, and this is the mesh 2 wherein I2 flows, and this is the mesh 3 wherein I3 flows. And we observe also that this is the current source which appears in common to two meshes, and this is also one more current source appearing in common to mesh 2 and mesh 3. So, after the observation, what we need to do is first write the constraint equation which actually relates the current source value with the corresponding mesh currents. Now, what we observe here, so from the circuit, first let us make sure of our objective once again. Vx we need to find, and we observe the positive polarity here, negative polarity here. So, always to find the Vx or any voltage across any resistor or any passive circuit element for that matter, you need to consider that particular current which enters the positive polarity. That current multiplied by the resistance or the impedance will give you the corresponding voltage. Now, in that way, you know, this particular arm only belongs to mesh 1. So, I1 flows in this direction. So, Vx is now given as I1 is the current which enters the positive polarity. So, it is I1 into 10 or simply 10 I1, right. So, now Vx is can be found by knowing the value of the mesh current I1. Now, as already told that we are observing two current sources. So, we write the constraint equation. Now, this is the current source value 3 amperes. It is also the effective current which flows in this branch. So, I2 is in alignment with that, I1 is in opposite direction to that. So, we can say I2 minus I1 is equal to 3. Okay. So, even if you apply, you know, I1 flows in this direction and I2 flows in this direction, and if you consider the 3 amperes to flow in this direction, if you apply KCL, this is what the relationship whatever we get, or simply this can be written as what, that particular current which is in alignment with the current source direction should be considered as positive, that particular current which is in opposite direction to that of current source should be considered to have negative sign. So, then in that case I2 minus I1 is actually equal to 3. And now, we will write this, our main objective is to find I1. So, we will write I2 in terms of I1, so that wherever we find I2 we will substitute that by 3 plus I1. Okay. You may also write, you know, I1 in terms of I2, but while finding the response values, first you will find the I2, then use this relation to find I1. But instead what we can do, anyway we want I1, so we will write I2 in terms of I1, then wherever I2 appears substitute 3 plus I1 to find the value of I1. Okay. So, in this way we can find the value of I1 directly. So, I2 is 3 plus I1. Now, one more, you know, now after the identification of the current source appearing in common to two meshes, after writing the constraint equation which gave you what I2 is equal to 3 plus I1, what we can also what we can do is we can club these two meshes and call it as super mesh. But what we also observe is this particular super mesh and this particular mesh shares this current source as common source appearing between them. So, what we will do, we will also write the constraint equation related to these two meshes, and finally what we can do is this super mesh and this mesh can be clubbed to form the overall super mesh, which is nothing but the outer loop. So, I2 is equal to 3 plus I1, done. Next constraint equation related to this. So, I3 minus I2 is equal to Vx by 4, or simply 4 I3 minus 4 I2 is equal to Vx, and Vx was found to be what? 10 I1. So, 10 I1. Right. Now, what we will do? We will we will use this. So, this implies 4 I3 minus 4 I2 is equal to 10 I1. Then I2 will be replaced by what? 3 plus I1. So, 4 I3 minus 4 I2 will be replaced by 3 plus I1. So, is equal to 10 I1. Now, this 10 comes here, this minus 4 into 3 will go to the right hand side. So, then in that case 4 I1 minus 10 I1, and this comes to the left hand side, plus 4 I3 is equal to 12. So, after arranging this equation properly, you will get minus 14 I1, then plus 4 I3 is equal to 12. Call this as equation 1. And this is the equation which has resulted from constraint equation, right. So, after writing the constraint equation, our next job is to apply what? KVL to the super mesh. Now, the super mesh is not this, but this overall outer loop, for the simple reason we first wrote constraint equation and clubbed these two meshes. Then we wrote constraint equation related to this current source, and then clubbed this mesh and this super mesh to form what? This outer loop to be a super mesh, right. So, then we will apply KVL to the super mesh. So, apply KVL to super mesh. Identify the super mesh now, as formed by so 10 ohms, then 2 ohms, then 4 ohms, then 25 volts, then 50 volts, then back to 10 ohms. So, let us start from here. So, we are going clockwise. So, 10 I1 plus 2 I2 here, then plus 4 I3 plus 25 minus 50 is equal to 0, plus 25 minus 50 is equal to 0. Now, what we will do? This can be written as 10 I1 plus 2 I2, then plus 4 I3 is equal to 50 minus 25, which turns out to be 25. Now, again we are writing I2 in terms of I1. So, 10 I1 plus 2 into I2, so which is 3 plus I1 plus 4 I3 is equal to 25. Now, 10 I1 plus 2 I1, so 12 I1 plus 4 I3, this 2 into 3 6 will come to the right hand side, becomes minus 6, 25 minus 6 is 19. Call this as equation 2. And solving 1 and 2, what we get? Solving equation 1 and 2, we get I1 as 0.2692 amperes, and then I3 as 3.9423 amperes. Now, you can find the value of I2 as 3 plus I1, but that is not required, since our objective is to find Vx, and finding of I1 is more than sufficient. Now, had this been written I1 in terms of I2, then wherever I1 was there, you would have substituted that in terms of I2, then finally you would have got the answer as what? In terms of I2 and I3. Then take that I2 and substitute in this relationship to get I1. Had I1 been written in terms of I2, but here we wrote, because we were knowing I1 is the one which is the most required parameter. So, we wrote I2 in terms of I1, so that I2 gets eliminated, and I1 what we actually require will remain in the equation. You can do otherwise also, but there will be one step extra, that is all. So, now I1 we have found. So, our objective is to find Vx, which is equal to 10 times of I1, so which will be given as 2.692 volts. Okay. So, now what we have done, we have used the concept of super mesh to find the value of V x, which was found to be 10 I1 and which was ultimately found to be 2.692 volts. Okay. Same thing has been written on the slides. So, from the circuit V x is equal to 10 I1, identifying 3 amperes and V x by 4 current sources appearing in common to 2 meshes 1 and 2 and mesh 2 and 3 respectively. The constraint equations are written as I2 minus I1 is equal to 3 implies I2 is 3 plus I1, then I3 minus I2 is equal to V x by 4. This is something related to mesh 2 and mesh 3 current source. Then we know that V x is equal to 10 I1, substitute this here to get finally this equation minus 14 I1 plus 4 I3, which is equal to 12. Then apply KVL to super mesh, then whatever I have written on the board, same thing is available here. So, 10 I1 plus 2 I2 plus 4 I3 plus 25 minus 50 is equal to 0. Then rearranging this equation, okay, with the substitution for I2 being equal to 3 plus I1, we get this 12 I1 plus 4 I3 is equal to 19. Solving 1 and 2, we get I1 as 0.2692, and this is the important parameter because our response, which is V x, depends on this. So, V x is equal to 10 I1, which is 2.692 volts. Okay. So, now we will take up the problem related to super mesh again, but this time it is the AC circuit. This time it is the AC circuit. Let us see how it goes. So, the problem has been already written on the board. Okay, the same problem. So, find V x. This is the V x which we need to find using mesh analysis, and this is the AC circuit. You can observe these are the AC sources, and there is reactive element here as well as here. So, our objective is to find V x using the mesh analysis. Okay, and one thing what we have to remember is, okay, when you are asked to find the solution using the mesh analysis, and in that case if you find a current source appearing in common to 2 meshes, you have to go for super mesh analysis to simplify the number of steps involved in obtaining the solution. And what we have to remember here is, it will not be asked like use super mesh concept. Okay, nothing like that will be mentioned. Okay, super mesh is also what? A case of mesh analysis, right? Okay, so we will take up this problem now. So, the same problem has been copied here. Okay, so our objective is to find V x using mesh analysis. Now, let us identify the meshes. As usual, there are 3 meshes here. So, this is the first mesh with the current I1, and this is the second mesh with the current I2, and this is the third mesh with the current I3. And Ix, whatever you are seeing here, it is the branch current or that current which flows through the arm which is common to 2 meshes. Okay, so what I want to tell you here is Ix is the resultant of I1 and I2. Okay, yeah. Now, what we want, that we should first identify, we want Vx, and Vx is now given as from the circuit. From the circuit, Vx is given as, positive polarity has been identified here. So, current I2 flows in this direction. Always what I have told, if you want to find the voltage drop across any passive circuit element, you have to consider that particular element which enters the positive polarity multiplied by the impedance of that passive circuit element, right. So, Vx is equal to that particular current which enters the positive polarity is I2, minus I2 rather, because I2 flows in this direction. So, minus I2 flows in this direction opposite to I2. So, minus I2, that means that particular current which enters the positive polarity into the impedance, so J4. So, Vx is ultimately minus J4 I2. So, this simply means that if we find I2, it is as good as finding Vx. Now, we also have to observe that there is a current source appearing in common to 2 meshes. So, what we will do is, we will identify the current source and write the constraint equation related to that. So, also from the circuit, so 2Ix is flowing in this direction. So, I3 minus I2 I3 minus I2 is actually 2 times of Ix. But what is Ix? So, Ix is now given as, it is the current which flows in this arm, and I1 is in alignment with that, I2 is opposite to that. So, I can write it as I1 minus I2. Now, what can be done is, so I3 is equal to 2 I1 minus 2 I2, this comes here plus I2. So, I3 is equal to 2 I1 minus 2 plus 1, so minus I2, right. So, this is the result of the constraint equation. So, if we apply KVL to the super mesh later, wherever we find I3, that will be substituted by this particular expression. So, we are eliminating one variable. At the same time, we are reducing one equation, right. So, I3 is equal to 2 times of I1 minus I2. Now, again whatever I have told earlier, same thing I repeat. Now, you could have obtained this in terms of I2, okay, but when you substitute for I2, I2 would be eliminated. So, then you would have found I3 first, then using this relationship you would have found I2, using this relationship you would have found out I2, right. So, here what we do, we eliminate I3 so that we can directly find I2, so that can be substituted directly here to find Vx. So, instead what you could have done, you could have written this in terms of I2, then substituted for I2, then I2 gets eliminated, and with the elimination of I2, what you will calculate first is I3 and I1, then using this relationship you come back and calculate what I2, then substitute here. So, it will be one step extra. In this case, we are doing it directly by eliminating I3, by doing the substitution for it, right. So, this is the result of the constraint equation. Now, apply KVL to super mesh formed by, okay, so J4 ohms, then 2 ohms, then 5 at an angle of 30 volts, okay, then come back here. So, minus J 2.5 ohms, then back to J4 ohms. Okay. So, as I was telling earlier, after writing the constraint equation, we club the corresponding meshes and call it as what? Super mesh. Then we apply KVL to the super mesh. Now, apply KVL to super mesh, then what follows? Let us start from here going clockwise. First you see what? Minus Vx, but writing minus Vx is also correct, but it will simply increase the number of unknowns. So, what we do, everywhere there is a potential drop, this has been identified, that is all. Had this been not identified, what you would have written? The same thing we will now write. So, plus J4 into I2, right. Even if you would have written minus Vx, minus Vx, the Vx would have been substituted as minus J4 I2, and it would have again become J4 I2. Then plus 2 I3, then plus polar form, keep 5 at an angle of 30 in brackets, then minus J 2.5 into I2 minus I1 is equal to 0, is equal to, okay. So, J4 I2 plus 2 I3 plus 5 at an angle of 30 voltage drop, then minus J 2.5 into I2 minus I1, okay, right. Now, you could have also written this as what? Minus J 2.5 into minus Ix, but again Ix will be replaced by what? I3 minus I2, which will again give you what? This itself, okay. Ix will be I1 minus I2, and when you replace that, you will get this itself. So, we are not writing the potential drop here in terms of Ix, because it will simply increase the unknowns. So, what we will do when we write minus J 2.5 into minus Ix, Ix will be replaced by I1 minus I2, and again we will get this only, okay. So, Ix is I1 minus I2. Now, arranging this equation, what do we get? First I1 terms, okay. So, plus J 2.5 I1, okay, then I2 terms plus j 2.5 I2 plus rather minus j 2.5 I2 plus j4. So, plus j 1.5 I2, okay, j4 I2 minus j 2.5 I2 1.5 j 1.5 I2, then plus 2 I3 plus 2 I3, then this one goes to the right hand side, becomes minus of 5 at an angle of 30 degree. Now, substituting I3 as 2 I1 minus I2, okay. So, j 2.5 I1 plus j 1.5 I2 plus 2, I3 is 2 I1 minus I2 is equal to minus 5 at an angle of 30 degree. And then what you observe? First accumulating I1 terms, 2 into 2, 4 I1 plus j 2.5 I1. So, it will be 4 plus j 2.5 I1. Then I2 terms, minus 2 plus j 1.5. So, minus 2 plus j 1.5 I2 is equal to, now in polar form it is 5 at an angle of 30 degree multiplied to minus sign. In rectangular form this will be equal to minus 4.33 then minus j 2.5 okay. So, yeah, everything is at right place. Okay, so call this as equation 1, and then what we will do here is we will apply KVL to mesh 1 to get another equation. We will apply KVL to the mesh 1, okay, and then in that case 10 I1, okay, and here minus j 2.5 into I1 minus I2, and then here polarities are not marked, but it is ensured that it is the voltage source and the arrowhead is given. This is the indicative of what the positive polarity here, negative polarity here. So, minus 20 at an angle of 0 degree is equal to 0. And now, what we will do here is this implies 10 I1 10 minus j 2.5 I1 plus j 2.5 I2, this goes to the right hand side and becomes 20. Call this as equation 2. Now, what we will do? We will use Cramers rule. Using Cramers rule, what is delta? Delta, it corresponds to what? The rows, okay. First row corresponds to the coefficients of the first equation, second row corresponds to the coefficients of the second equation, okay. Then what I can do here? So, delta is equal to, so 10 minus j 2.5, so j 2.5, and then 4 plus j 2.5, then minus 2 plus j 1.5, okay, right. Now, in this case what I have done is, instead of writing the first equation coefficients in the first row, okay, I have written the second equation coefficients in the first row, but still not a problem. While substituting the sources, what we need to do is substituting the RHS. First you have to substitute what? 20, then followed by this, that is all, right. So, delta is now equal to 10 minus j 2.5 into minus 2 plus j 1.5, then minus j 2.5 into 4 plus j 2.5, then delta will turn out to be, okay, delta will be equal to minus 10 plus J10, minus 10 plus J10. So, this is the delta. Now, what I need to do, our objective is to find Vx, and Vx depended upon I2. So, we need to find I2. So, delta I2. So, the right hand side should be substituted in the second column. So, writing the first column of delta as it is 10 minus J 2.5, 4 plus J 2.5. Then the right hand side, you know what I had done, the first row had been the coefficients of the second equation here. So, what I need to do, even the right hand side, when you are substituting in the second column, the element corresponding to second equation should come as first element. So, 20, and then here minus 4.33 minus J 2.5. Okay, so then this is equal to 10 minus J 2.5 into minus 4.33 minus J 2.5, then minus 20 into 4 plus J 2.5. Then delta I2 will be calculated as, okay, when you substitute this in the calculator, so you will be getting delta I2 as minus 129.55, then minus J 64.175. So, you got delta I2 now. So, now what I need to do is, I need to find I2, which is delta I2 divided by delta. So, which is equal to, in brackets, okay, minus 129.55, then minus J 64.175, then whole divided by, you know, minus 10 plus J 10. Okay, you are strictly speaking, you know, when you take the division of complex numbers, it has to be in the polar form, but your calculators can even do it when the complex numbers are in rectangular form. Only the thing is you have to use the brackets. Then I2 you will get it as, you know, 3.268, then plus J 9.68. Okay, so which in polar form can be written as 10.22 at an angle of 71.35 degrees amperes. But this is not the end of the problem. We need to find Vx, okay, which is anyway easy. So, Vx is now equal to, as already written, it is minus J4 I2, minus J4 I2. So, minus J4 into, in brackets, 10.22 at an angle of 71.35 degrees. So, when you substitute this, you will get Vx as 38.745, then minus J 13.075. Then Vx in polar form is written as 40.89 at an angle of minus 18.64 degrees, okay, volts. So, this is the expected result, right. So, what we have done, we have found Vx using the mesh analysis, but we used the concept of super mesh since there was a current source appearing in common to these two meshes, right. So, that ends the problem. Now, how we have super mesh concept in the case of mesh analysis? In the same way we have super node concept in the node analysis, and in the, when we actually apply the super mesh concept, whenever a current source appearing in common to two meshes. Now, when we apply the super node concept now, whenever there is a voltage source appearing in common to two nodes, it will always be advantageous to find the solution if we consider the concept of super node whenever there is a voltage source appearing in common to two nodes, right. Okay. So, we will see that. Now, let me illustrate how the concept of super node will be advantageous in node analysis whenever a voltage source appear in common to two nodes. Let us consider an example. Say this is Is and then R1, then there is a voltage source Vs R2 and then R3. Now, let us find the solution using the node analysis, and our preliminary objective in the node analysis is to find the node voltages. So, we will find the node voltages. How? First by the usual method of node analysis, then we consider the concept of super node, since there is a voltage source appearing in common to two nodes, and then we will observe that there will be reduction in number of steps in obtaining the node voltages when we use the concept of super node. Right. So, now so this is the ground node. So, leaving this ground node, there are two nodes V1 and V2. Now, we will apply the node analysis, the usual node analysis method to find V1 and V2. So, apply KCL at node 1. What is the current that comes out of this node in this direction? Minus Is. What is the current that comes out of this node in this direction? So, V1 by R1. What is the current that comes out of this node in this direction? Now, the current, had there been a passive circuit element, you would have written V1 minus V2 divided by R. Supposedly, there is a resistance there, but there is a voltage source. The current, whatever that enters or leaves this voltage source, depend upon the circuit that is connected across its terminals, because they act as load to this, which we do not know right now. So, what we will do? We will assume a current to flow in this direction, Ix. So, minus Is V1 by R1, what is the current that comes out of this node in this direction? Plus Ix is equal to 0. And this can be arranged as V1 by R1 plus Ix is equal to Is, call this as equation 1. V1, Ix both unknown. Is is known quantity because it is a current source. Now, similarly, apply KCL at node 2. So, we only strictly follow the statement of the KCL. The algebraic sum of the branch currents that leave a node is equal to 0. So, what is the current that comes out of this node in this direction? V2 by R2 and plus V2 by R3, which is the current that comes out of this node in this direction. And what is the current that comes out of this node in this direction? It is minus Ix is equal to 0. And now, we can rearrange this equation to be written something like, so this implies V2 by R2 plus V2 by R3 is equal to Ix, call this as equation 2. But what we can do is substitute 2 in 1, substitute 2 in 1 to get what? To get V1 by R1, and then plus Ix is there, so that will be replaced by this. So, V2 by R2 plus V2 by R3 is equal to Is, call this as equation 3. Now, what we should not say is that there are 3 equations and 3 unknowns, where unknowns being V1, V2 and Ix. That should not be said, because when we write this equation, this has been obtained from 1 and 2. So, when we write this 1 and 2 become redundant. So, we need to find some other equation. Now, in this equation there is one equation, 2 unknowns V1, V2. So, we need to find the other equation, which anyway which is very much evident from the circuit. What we observe here is the potential difference between these two is Vs with this as reference. So, then in that case, from the circuit, so V1 minus V2 is equal to Vs. Now, you can write this as V1 is equal to V2 plus Vs, call this as 4. Then substitute 4 in 3 to get what? To get, when you take this V1 as V2 plus Vs and substitute here, you will be evaluating what? V2, and substitute V2. After obtaining V2 from this equation, you will substitute that in 4 in equation 4 to get V1. So, this is how we calculate the node voltages, and as already told, if you know the node voltages in a network, you can find the response at any point of network, and sometimes the node voltages themselves will be the response of the network. Now, we will apply the concept of super node, applying the concept of super node. So, what we do, just as what we did in the case of super mesh, we will identify that there is a voltage source appearing in common to two nodes, okay, and write the constraint equation, which is the equation that relates the voltage source value with the corresponding node voltages, right. So, then in that case, so from the circuit, okay, so we write V1 minus V2 which is equal to Vs, and this can be immediately written as V1 is equal to V2 plus Vs. So, we got this equation 1 now. Now, what we do, after, just like in the case of super mesh, after writing the constraint equation, we clubbed the corresponding meshes. So, here we club the corresponding nodes and call it as a single node called as super node. So, these two nodes are clubbed and called as a super node X. Now, this super node X has got how many branches? 1, 2 on this side, 3, 4 on this side. Okay, there are 4 branches associated with this super node. And please remember, there is no separate node voltage allocated to super node. On this side of the super node, it is V1 being the node voltage, and on this side of the super node, the voltage here will be still V2. Okay. And now, after clubbing the corresponding nodes and calling it as super node X, we will apply KCL at super node X. Apply KCL at super node X. So, what is the current that comes out of this node in this direction? Minus Is. What is the current that comes out of this node in this direction? V1 by R1. What is the current that comes out of this node in this direction? V2 by R2. And what is the current that comes out of this node in this direction? It is V2 by R3 is equal to 0. Now, this can be written as V1 by R1 plus V2 by R2 plus V2 by R3 is equal to Is. Call this as equation 2 in this case. Now, when we consider the equation 2 here and the equation 3 here in the previous case, they are same, but we got this equation 2 in an easy manner, whereas this equation 3 was obtained by writing equation 1, equation 2 and then substituting 2 in 1, then we got this, whereas applying the concept of super node, we got it straight away when we applied KCL at super node X. Okay, so this has application of concept of super node has reduced the number of steps, no doubts in that. So, what we do now, just for the sake of formality, we complete this problem now. So, what we do, V1 is equal to V2 plus Vs, take this as 1, okay, substitute for V1 in 2. So, substitute 1 in 2. So, then this indicates V1 being equal to V2 plus Vs will be substituted here to get V2, then substitute V2. So, when we substitute V1 as V2 plus Vs here, we will get the equation only in terms of V2, which can be solved to get the value of V2. Then obtained value of V2 will be substituted in equation 1. Substitute V2 in equation 1 to get V1. So, that is how you find the corresponding node voltages using the concept of super node. So, definitely whenever a voltage source appears in common to two nodes in the node analysis, applying the concept of super node greatly reduces the number of steps involved in obtaining the solution for that problem. Okay? Right. So, now we will see a problem related to the super node. Now, we will consider a problem related to the super node. Now, this is the problem. So, what we need to do here is find IA and VA in the network shown in figure 23. This is the figure 23 using node analysis. Now, again what we have to remember is the problem will not be asked like use super node concept or by super node analysis, nothing like that. It is left to us to identify that there is a voltage source appearing in common to two nodes like in this case, right. So, now the same problem will be copied to the board. So, we will try finding the solution. Okay. So, here comes the problem. So, 500 ohms, then 125 ohms, 12 volts, 250 ohms, 500 ohms plus minus VA, and then there is plus minus 8 volts, right. And what we are asked to find? We are to find IA and VA. Okay, IA and VA. What are the values of these? And that we have to find using node analysis. Very simple. First, let us make sure what we want. So, we want IA and VA, and let us express them in terms of node voltages, that is all. Okay, first let us identify this node to be the ground node. So, this is the ground node. Leaving this ground node, there are 3 node voltages, or rather 3 nodes. Associated voltages are given by V1, V2 and V3. And from the circuit, now what we want? IA. IA is the current which flows in this direction. So, this potential minus this potential divided by 250. So, V2 minus V3 divided by 250. And what is VA? VA is after all the potential difference between this point and this point with this as reference. Okay. And what is V3? It is the potential difference between this point and the ground point, or this point with this as reference. So, I can say VA is nothing but V3. So, this problem gets solved, okay, when we find what? V2 and V3. Okay. Now, we have to be very good observers, right. So, what we observe here is, from the circuit, also from the circuit, V2 is the potential difference between this point and this point with this as reference. And what is 12 volts? 12 volts is the potential difference between this point and this point with this as reference again. So, what we can say, V2 is straight away 12 volts, V2 is straight away 12 volts. Okay. Right. Now, we also observe that there is a voltage source appearing in common to this particular node and this particular node. So, what we will do? We will write the constraint equation. What is that? That is the equation which relates the voltage source value with the corresponding node voltages. And this being at higher potential, what we can write is V1 minus V3 is equal to 8. And now, we want V3 actually. Okay. So, let us write V1 in terms of V3. So, V1 is equal to 8 plus V3. So, that wherever V1 we find, we will substitute in terms of V3. So, that V3 can be directly evaluated, that is all. So, V1 is 8 plus V3. Now, after writing the constraint equation, we will club these 2 nodes and call it as what? Super node X. Now, apply KCL at super node X. So, what is the current that comes out of this node in this direction? It is V1 by 500. And what is the current that comes out of this node in this direction? We consider only the leaving currents. So, V1 minus V2 divided by 125. And these 2 branches here corresponds to the super node, and these 2 branches here corresponds to super node. So, what is the current that comes out of this node in this direction? It is V3 by 500. What is the current that comes out of this node in this direction? It is minus IA, no doubt, but it can also be written as V3 minus V2 divided by 250, which is ultimately equal to 0. Now, the LCM very much obvious, it is 500. So, this implies, the LCM is 500. So, V1 plus 4 V1 minus 4 V2, because 125 goes 4 times in 500, plus V3, then plus 2 V3 minus 2 V2, okay, is equal to 0. In the next step, this 500 will multiply this 0 and eventually be 0. So, this implies, V1 terms 4 V1 plus V1, so 5 V1, then minus 4 V2, then plus 3 V3. Okay. Let us check once again, V1 plus 4 V1, 5 V1, V2 terms there are 2, minus 4 V2 minus 2 V2, so it should be 6 V2. Then V3 terms there are 2 V1, I mean 1 plus 2 3 V3, right. So then this is equal to 0. Then what we need to do, we need to substitute V1 as, here you can observe V1 as 8 plus V3. So 5 into 8 plus V3 minus 6, and V2 also we have in the very beginning written it as 12. So 12 plus 3 V3 is equal to 0. Now you have what? Everything in terms of V3, okay, 5 V3 plus 3 V3, 8 V3, and the constants, minus 6 into 12, 72, minus 72 goes to the right hand side, becomes plus 72. 5 into 40, sorry, 5 into 8, 40, goes to the right hand side, becomes minus 40. So 32. So this implies V3 is equal to 32 by 8, so which is 4 volts. So what we have done now, V3 we have found, and already V2 we have. For our response IA VA, only V2 V3 we require. So IA is now equal to V2 minus V3 by 250. So which is equal to V2 minus V3 by 250. V2 is 12, V3 is 4 by 250. So it is 8 by 250. 8 by 250 is 0.032. Okay, 1 by 250 is 0.004 into 8 should be 0.032 amperes. Then this implies IA is 32 milliamperes. So IA we have found, and what is after all VA? VA is V3, so which is equal to 4 volts. Okay. So now what we have done is we have used the concept of super node, and we were able to obtain in an easy way the values of IA and VA here. Okay. So let me repeat that when the problem is given, it will not be asked like use the super node analysis. It will be still given as node analysis. It is left to us in identifying that there is a voltage source appearing in common to two nodes, and then writing the constraint equation, clubbing the corresponding nodes, and then calling it as super node, and then applying KCL at super node. So this will essentially reduce one equation and obviously reduce the number of steps involved in obtaining the solution for a problem, right. Okay. So today what we have done is we have looked into the problems of super mesh, based on super mesh, and we discussed the illustration of the concept of super node being applied to a typical node analysis problem, wherein we observe that the application of super node concept reduces the number of steps involved in obtaining the solution, and a problem related to the super node. Okay. So which was this itself. So find IA VA. So the same thing has been written on the slides, we may observe there. Okay. So from the circuit, IA is V2 minus V3 by 250, VA is V3, then V2 is equal to 12 volts, okay, straight away. Okay. Then V1 minus V3 is equal to 8, this potential minus this potential is 8 volts. Then writing V1 in terms of what? V3, 8 plus V3, then applying KCL at super node X. So we get this particular equation. When we properly arrange, this is what we get, and substituting V1 as 8 plus V3, we get this. Then the equation will be simplified to this, and when we substitute V2 as 12 here, so V3 will be found as 4 volts. And then we recall the expressions of IA and VA, and then substitute properly the values of V2 and V3 to get IA as 32 milli and VA as 4 volts. Okay. So tomorrow in the next class, what we will do is we will continue with the problems of node analysis wherein we will be applying the concept of supernode, and then what follows will be the star to delta transformation and delta to star transformation, right, and that will be the last topic of the module 1. We also discuss the problems related to star to delta and delta to star transformations. Okay. So, with this the lecture comes to an end. Thank you.